The next study is going to be talked about as a density management study. Paul Anderson is a research forester with the PNW Research Station here in Corvallis. And another observational study, and see what you think about extrapolating that one. Help me welcome Paul Anderson.
All right. So good morning. I took some liberties already with this presentation. Cheryl asked me to talk about what the density management has taught us about buffers, and I took the liberty of saying it's what it's teaching us about buffers. It's still ongoing, it's still active. Also, I've added Dede Olson as a co-author, and the reason for that is Dede and I have been sort of working collaboratively on the density management studies for many years now, and when it comes down to what do we know about buffers, a lot of what we know about buffers relates not only to the kind of the microclimate and microhabitat elements that I've been looking at, but also the wildlife and that uses that habitat and experiences those microclimates. Let's see if I can get this correct. All right. So my approach here is just to kind of use this slide just to acknowledge that the full title of the density management studies is the BLM Density Management and Riparian Buffer Study. And really, if you think about where this came about, came about from an interest in understanding whether or not enhancing structural and biodiversity could be accomplished through active management. And this panel of images simply illustrates the nature of the forests in which this this study was being conducted. And so it's looking at primarily in BLM lands and some of their young second growth Douglas fir forests, basically in that 40 to 60 year age group where there's interest in doing some active management. And the question of, can you take these relatively uniform, even age stands and enhance their functionality in terms of meeting some broader array of ecological goals. So by doing some manipulations to create maybe things like gaps, doing some thinning in order to create opportunities for enhancing understory development. And so originally the density management studies was set up around some of these terrestrial questions, but when they went to lay out treatments to try out different things, they kept on having this problem of encountering streams in their units. And so given that with the aquatic conservation strategy that came about with the Northwest Forest Plan, there was interest, all right, well, can we take advantage of this and embed another element to the overarching terrestrial question and look at how we might manage within those riparian reserves to accomplish some restoration objectives. So I'm really only going to be talking about the riparian component. And basically this kind of goes back to some of the discussion that Dede presented earlier about riparian reserves and their role in conserving diversity, maintaining stream habitat and water quality, and providing connectivity. And the question is, can you meet those riparian reserve objectives while perhaps adding something else to enhance riparian functionality? And so can we go into those riparian reserves and accomplish some restoration strategies? So we also saw earlier the FEMAT description of sort of how we might be influencing some elements such as like microclimate when we go in and do some of these types of restoration harvest activities. And all I'm going to point out here, since this diagram was explained earlier, is I'm going to be talking today about air temperature, soil temperature, air temperature, and relative humidity in the work that we've done on the density management studies. I'm also going to be talking a little bit about some of these other functions as we go along in terms of thinking such as shading and coarse wood debris inputs to streams. So describing what we've learned a little bit about that. So there were, as I mentioned earlier, there were some objectives associated with the terrestrial component of the density management studies, but what we're focusing on here this morning is really trying to assess the combined effects of density management and alternative riparian buffer widths on aquatic and riparian ecosystems. Density management studies is sort of this hierarchical study design. And what this diagram illustrates is one site, the Green Peak Density Management Study site, which is just a little bit to the west and south of here. What the DMS study consists of is every area has a control or an unthinned unit. So again, remember, these are all in these young 40 to 60-year-old stands. But then there's some additional thinning treatments that were of interest to the terrestrial component. One was implementing what we're calling a moderate density thinning. So that's taking the unthinned density of about 220 trees per acre down to a target level of 80 trees per acre, and that's what this green is. There was interest in what would be the impact of a less intensive thinning, so bringing it down to 120 trees per acre. And then the impact of mixing within a stand size unit, 3 different levels of thinning, a high density retention, a moderate density retention, and a low density retention, bringing it down to 40 trees per acre. And then embedded in all of this to create another scale of heterogeneity is the inclusion of either leave islands, areas where you skip over during the thinning operation, or gaps where you actually do a small group opening. And leave islands and group openings were 1/4, 1/2, and 1 acre in size, and applied to about 10% of the area in each of those stands. So that's what the overarching terrestrial question was. Our interest, however, was in looking at these alternative riparian designs. And we already talked about the 2 tree height and the 1 tree height riparian reserve interim guidelines for fish-bearing and non-fish-bearing streams. What the density management study added was a couple other delineations, and these kind of merged towards some of the buffer descriptions that Jeremy provided for the state and private lands. But in a sense, we have this 20-foot wide minimum stream side retention buffer, which was really intended to function to preserve those near stream attributes of bank stability and direct shading and direct wood input. What that is it's a minimum of 20 feet wide, or retaining any tree along the stream side that had a portion of its canopy extending over the channel. Then also, the other alternative buffer design was a variable width buffer design, and you can think about this as a buffer that had a 50-foot minimum but would extend out to encompass distinct riparian features or features of interest or sensitivity. So it might expand outward to encompass a marshy area. It might extend outward to encompass some plants or species of interest, or some unstable slope banks. So within the density management design, then, we looked at these buffers primarily in the 80 tree per acre, and then at a given site, we would try and implement all 4 buffers, but at the case of Green Peak, we didn't have enough streams to implement the 2 tree height buffer. So depending upon what site we're at, you might have a little bit different suite of buffers. And then also, in terms of where this study was conducted, there are a total of 13 sites, or 12 sites illustrated here, but 7 of these sites were initial thinning sites, and 5 sites were rethinned sites. Didi's work that I'll be speaking to later incorporates almost all of these sites, plus 3 additional sites on Forest Service lands, and the microclimate and downed wood work that I'll be speaking to was focused almost entirely on those sites in the blue. So I'm going to just talk about some key findings kind of quickly, really kind of getting into some of the sort of the overarching results. And mostly these results are from sort of the 3 to 5 years after initial treatment phase. So we're going to be talking about canopy closure, microclimate, habitat, and some information on animals. So what did these stand conditions, what did these treatments do in the overstory? And what we're trying to illustrate here is that this is an image of these hemispherical photographs. A couple speakers have already spoken about these. But basically what we want to illustrate is just the array of light conditions that were created by these different structural elements in the overstory. And so at unthinned stands, we're talking about 9% of visible sky with that 80 trees per acre thinning, that moderate density of thinning. We have about 28%. In this case, a 40 tree per acre, a low residual density, brings it up to about 38%. And a 1 acre patch, so the biggest group opening, still only generates about 61% of full sky. So when you take this, we can relate it back to changes in basal area. And the key point here is that at basal areas above 120, there's pretty flat response in terms of the amount of visible sky that's apparent. You really, once you start lowering the basal area below 120 square feet is when you start to really increase that amount of visible light and putatively the amount of radiation intercepting or transmitted to the forest floor. So when you take a look at what did it mean in our study system, then what we have here in this diagram, and you're going to see this panel of diagrams are all constructed the same way. I've broken the landscape down into the stream zone, the buffer zone. So this is the buffer zone is delineated by either a 2-tree height, 1-tree height, stream side retention, or variable width, and then the upslope thinned portion of the stands. And what these, what the results indicate, it always is in the same order. From left to right, you go from unthinned to wide buffers adjacent to thinning, wide buffers with an adjacent patch opening, a variable width buffer, thinned, variable width buffer adjacent to a patch opening, and then a stream side retention buffer adjacent to thinning. And so all we're showing here in this panel is basically the changes in basal areas are occurring associated with the thinning operations. And what does that mean in terms of percent visible sky? So in the stream, even though we didn't measure basal area, we did measure visible sky, and we're seeing that these narrow buffers, as well as a variable width buffer adjacent to a patch opening, you do have elevation of percent visible sky. So you're getting increased light transmittance and energy transmittance. Similarly, within the buffer, we're getting some separation of these treatments, again, only with these relatively narrow buffers or the variable width buffer adjacent to a patch opening. And then in the upslope, you see the clear distinction between the patch openings and the thin stands and the control. So how does microclimate relate to some of this type of the patterns? And so this just shows for unthinned stands, and all the microclimate stuff I'm going to be presenting is really looking at late summer peak temperature season results. And so this just shows those patterns. So if you remember that FEMAT diagram, which shows those trends with distance from stream as these long sloping lines, we can get a sense of what's going on in a unthinned stand, for example, with respect to air temperature. You have some relatively steep increases in temperature in the first 50 feet or so, and then it pretty flat in terms of temperature range as you go upslope from there. Relative humidity shows a much more pronounced or protracted decline over distance. And then soil temperature, and in this case, in the stream channel, that's actually the stream bed temperature, we see a sharp increase up to between the stream bed and the stream side, but then very little change over distance. But what happens when you actually implement these treatments? And this is where we're starting to make some inferences about the influence or the effectiveness of buffers. What we see in this diagram is in the upslope where we had the thinning occurring, we do get some increases in maximum air temperature, pretty substantial ones associated with patch openings. There's a lot of variability, so they don't really separate out that strongly. When you get into the buffer where you're seeing differences occur, you have either the patch openings associated with a B1 buffer, a patch opening associated with a variable width buffer, or the narrowest stream side retention buffer being elevated relative to the control and the other buffer treatments. It's important to note here, though, that we don't have much separation, or at least statistically in this case, we don't have separation between a variable width buffer that's adjacent to thinning or a B1 buffer adjacent to thinning relative to unthinned stands. And then when we get into the stream, we're seeing this array of mean responses, and where we get the real elevation is really only with this stream side retention buffer. Although you can see the array of maximum temperatures ranges from about 17 degrees to about 19 degrees. So there's about a 2-degree range in terms of those mean values. Interesting to note that given these, the amount of variability and whatnot, though, the unthinned reaches actually tend to have higher maximum air temperatures than some of our other buffered reaches, but within that range of variability. So we also tried to get a little bit at stream temperature with our data set. And I have to explain about what we're calling stream bed temperature. Is in the stream, we have these temperature probes that were actually embedded in the stream bed from a depth 0 to 15 centimeters deep. So it's a long metal probe. So basically what we're doing is measuring the temperature of the saturated stream bed in lieu of having a distinct measurement of water temperature. But again, in these maximum stream bed temperatures within the stream zone, we're not seeing much elevation or much differentiation in terms of stream temperatures associated with any of the treatments. And again, the unthinned reaches that were included in this study tended to have slightly higher mean values than either the one tree height buffered reaches or the variable width buffered reaches. So again, kind of pointing back to some of the things that Steve has said earlier, where you know, the signals can vary quite a bit based on the individual reach conditions. And so some of that expectation about harvesting and whatnot doesn't necessarily lead to consistent trends of elevated temperatures. So just in terms of some summary statements, some key things, we did see some relatively strong gradients in terms of microclimate within 10 meters of the stream. It appears to be a zone in which the stream is exerting a strong influence on near-stream microclimate. One of the conclusions that we came to is that the variable width buffers appear to be sufficient to mitigate thinning effects on microclimate above the stream. The caveat there is every once in a while when you get a patch opening directly adjacent to that buffer, then that adds more variability and has a potential to influence those temperatures. But there was no apparent increase in mitigation effectiveness associated with the wider buffers. So those 1 tree height and 2 tree height buffers on our small headwater streams really didn't seem to add a lot relative to the variable width buffer. So another step that we've taken with this data set is gone to doing some spatial modeling of riparian microclimate. And so one of the elements that is a little bit different than the previous two talks is that our concerns extend from the stream all the way up slope. And so we're trying to develop some ways that we might be able to enhance our ability to either monitor or to model the influences of buffers, thinning, and their impacts on microclimate in this transect that runs all the way from the stream to the ridgeline. But some of the things that you might expect, the big predictors are distance from stream and height above stream. On some reaches, we have vegetation influences kicking in, but for the most part, we were successful in generating some reasonably good models of spatial variation in riparian microclimate using a technique of kriging, but employing some additional covariates. So then the other question that we're trying to look at is what are some of the factors influencing the effectiveness of buffers as a source of shade? So obviously there's a lot of interest right now in terms of setting some guidelines for how we might manage the thermal loading within streams and their potential impacts on stream temperature. So there are obviously these things about stand structure that we've spent a lot of time looking at with our overstory treatments, but there's also elements of topography, stream orientation, things like channel profile and channel width that come into play, as was spoken to earlier by Steve. And I just wanted to point out, and we did on a subset of reaches, we did some highly detailed stem mapping and coupled that with some measures of in-stream radiation and hydrologic or topographic characteristics. And one of the things I just wanted to point out there is on these very small headwater streams in which we're dealing with, and with the relatively high degree of canopy closure, we're seeing really pretty low degrees of correlation between air temperature, or between our measures of radiation. Basically, this is percent visible sky, is pretty weakly correlated with any of our measures of either minimum street temperature, daily maximum street temperature, or daily ranges of stream temperatures. We tend to find a little bit stronger correlations between our microclimate variables with things like stream orientation, and some of the topographic features also are represented here, but they're not coming out very strongly. So again, the notion of looking at just canopy closure as an index of some predictive value in terms of coming up with measures of air temperature or its impacts on stream temperature, fairly weak correlation in these small headwater streams. And so just want to talk a little bit about the headwater habitats that we've been dealing with. And these are truly headwaters, so we're dealing with our portions of that network where we may have intermittent discontinuous streams as well as continuous streams. And they're really kind of the habitats that we're going to be talking a little bit about in terms of salamanders, some of the frogs, tailed frogs, I guess, as well as some fishes. And so just to kind of reiterate, Dee Olson, in part of her project, has gone through and characterized the flow regime, seasonal flow regime for many of the streams within the density management studies sites. And looking at 131 different reaches, most of these reaches come out in sort of this, either sort of a seasonally wet followed by a seasonally wet, or a seasonally wet followed by a seasonally intermittent, or a lot of them are seasonally intermittent. So in other words, both spring and summer intermittencies. So they're spatially intermittent as well as seasonally intermittent. So this is the nature of the streams that we're kind of dealing with. Another habitat influence is the amount of wood that's going into these streams. And again, my rather complex diagrams, but what we found after five years of post-harvest monitoring in these studies is that looking at coarse wood deposition, what we're seeing comparing the buffers prior to treatment and buffers 5 years after treatment, the only changes that we were observing in some of the work that I was associated with was sort of a tightening up and basically a reduction in the amount of variability, with some of the reaches that had a lot of high abundance, that abundance declining somewhat. Not really a lot of response at all in terms of the upslope wood deposition. Dee's been looking more at wood in the channels and what the source of that wood is, and she's got data coming through 9 years of harvest now. And you can see here where she's with the variable width buffers, streamside retention buffers, and control buffers, the volumes of wood that are occurring in those different buffer types and where it comes from. So most of the wood is coming from the floodplain. There's another strong proportion of the wood coming from the active channel, and generally there's low potential from the wetted channel itself or from the wood spanning the wetted active channel. So, and you can see that there is recruitment of wood coming, and again, a lot of that is coming from the floodplain. Dee's assessed the occurrence of 13 different species of amphibians and 5 different species of fishes. And some of these amphibians are ubiquitous across the multitude of sites that she's looked at. Others are rather site-specific or occur only at a few sites. And so probably not going to do complete justice to her work. But the important things coming out of Dee Dee's work are how these different organisms form different assemblages in different portions of the riparian or headwaters landscape. And so there are distinct assemblages that are associated with the stream banks, the upslope, and then sort of the intermittent portions of the stream versus the perennial portions of the stream. And a lot of that variability, those assemblages, basically there's different levels of diversity in terms of the different types of species that occur near streams versus the upslope conditions. And then those different assemblages can be associated back to either ephemeral streams or perennial streams, ephemeral ponds, perennial ponds, or bank organisms, as you can see here. So again, the key things here in this diagram, panel diagram, is again illustrating differences in these assemblages associated with dry, intermittent, and perennial streams, and whether these are stream bank organisms or in-channel organisms. And again, just showing this development of different assemblages and how those assemblages occur in sort of that background landscape. But then what happens when you apply treatments to these landscapes? How do these assemblages respond and these organisms respond? And so Dee Dee summarized some of her results from several papers on this slide. And basically, in the first couple of years, these stream habitat and stream and bank animals tend to have relatively no negative treatment effects. If we look at some of the upland salamanders, you start to see some variability in terms of some sites yes, some sites no, so a site specificity. And then in the years 1 through 5, you tend to, again, have mixed treatment effects. Stephanie Wessel did some work looking at leaf islands and the occurrence of these animals in leaf islands, and so we see some differences in those leaf islands in terms of those abundances. And then also, the important finding from the leaf island study is that they have interior microclimates. So is a 1 acre leaf island suitable for creating an interior environment? And then in terms of a little further along, years 5 and 6, there was some indication in stream and bank animals that you have fewer bank planthodon. I'm going to mispronounce it. What is it?
Western redback salamander.
Thank you. And then in terms of the upland salamanders, no treatment effects or some distance from stream effects. So there's a lot of caveats in terms of some of the organism work in terms of detectability issues when you have relatively infrequently occurring individuals as well as infrequently occurring species. There's power issues associated with the statistical analysis on these organisms. And then there's always a spatial scale interest issue. And so Dee Dee wants to make sure that the inference of these findings are really restricted to the study sites. So from Dee Dee's work, we came away from sort of this notion that there's some strong multiple headwater vertebrate assemblages. There's no real dramatic thinning or buffer effect so far. Some patterns with bank and some patterns in terms of the bank and upland salamanders, and then we're continuing with a phase 2 that we can talk about later. Good.